go. Okay, so the first of these example problems we're going to look at here is going to be on, this is number 19. This is not assigned for the homework, but it's still a good problem to go over. And we're given for number 19 that y is equal to pi over 2, is it sine? Yeah, sine theta minus cosine theta. Like so, okay? And so what we want to do here is come up with the derivative of it. But wait a minute, it's got thetas, not x's. Is that going to change how we do things? No, it just means now that our independent variable is theta, not x. So when we take the derivative of this, we'll take it with respect to theta instead of respect to x. How you could tell when this happens, okay, is they'll probably write this out as y prime equals, but they may instead, or you may instead write the derivative as d over d theta, okay, instead. So if I did it that way, this is saying I'm taking the derivative with respect to theta now, okay? So what's the derivative with respect to theta come out for this thing? It's pi halves times cosine of theta minus sine of theta. So all cleaned up.
You don't have to write the x.
You mean the d theta in this case?
D theta, yeah.
No, because what's the d theta going to be?
That's nothing.
Well, it's 1 in this case. Because what's the derivative of theta by itself? 1. That d theta, if you remember, is just telling you if the argument of my sine or cosine is something not simply theta or x or something like that, then to account for it, I multiply it by the derivative again. Okay?
Why did you switch the sine, cosine already?
I didn't switch them. I took their derivatives. Remember, what's the derivative of the cosine? Minus the sine. And what's the derivative of the sine? It's positive cosine. So basically, Teddy, what I'm doing there is I'm using those special rules we learned for just the sine and the cosine to come up with this thing's derivative. Okay? By the way, it's very important to note, okay, what I'm taking the derivative with respect to. Okay? Because it turns out if I have a variable in my equation that's not one of the ones I'm taking the derivative that's not one of the ones I'm taking the derivative with respect to, okay, then what I end up getting there is I treat that extra variable as a constant, and it would go to 0. Let me give you an example of what I mean by that, okay? So, basically the rule here is any variable that is not the variable we are taking the derivative with respect to is a constant in this case. It's treated as a constant, I should say. It's not a constant, but it is treated as a constant. Okay. Okay. So, an example of that, let's say I've got f of x equals 3x to the 4th minus 2z to the 7th. Okay? If I ask you for f prime of x, the z is a constant because I'm not taking the derivative here with respect to z, I'm taking it with respect to x. Okay? Hence why it says f of x, not f of z. So, when I take the derivative, 3x to the 4th works out normally with derivatives. What's it going to be?
12x cubed.
12x cubed.
Minus 2z.
Okay.
Will
Would it be minus 2z to the 7th? What's the derivative of a constant?
0.
So, if z is going to be treated as a constant here, it would be 0. So it's actually minus 0. Okay? It all goes to 0 because that's a constant in this case. Alright? Another example of this, just to kind of hit home with the whole it's treated as a constant. Let's say I do the derivative with respect to x of 5x squared z to the third minus 10x plus 4z. That's for this derivative here. Okay. The 4z at the end goes to 0, right? The minus 10x would just be derivative of minus 10. But this guy right here, the z here, if it's a constant, do I do anything to it when I take the derivative? Well, if it was by itself, it would go to 0. But there's an x with it now, so it stays the same, right?
So you just leave it.
You just leave it. So this thing actually, its derivative would become 10 z cubed x minus 10 plus 0. Okay? Essentially, this thing is treated as a constant. Okay? And so you treat it just the same way you do any constant. So in that case, it becomes a scalar multiple. Okay? Is that clear kind of how that works now? Yeah. Do keep that in mind when looking at these things. Okay? All right. Good. What we're going to do now is we're going to move on and we're going to learn the next two sets of differentiation rules. Okay? That we're going to work with. Okay? Here's the deal. So far, we've got rules for doing basically dealing with constants. We have rules for, we got the power rule to deal with derivatives in general. If we have a scalar, we know how to handle those. And if we're adding or subtracting two things I'm taking the derivative of, we know how to handle those, right? Just take the derivative of everything separately. Okay? All of these come from limits. All those rules come from limits and make life easy for us. Okay? The next two rules have to do with what happens when I'm multiplying things I'm taking the derivative of, or dividing things I'm taking the derivative of. Okay? And it turns out that those rules aren't as straightforward as the other ones are. Okay? In fact, they actually get their own special rules to go over. Okay? So let's start with the first one. Let's start with what happens when I have two functions that I'm multiplying together. Okay? And I want to come up with the derivative of them. Okay? So my two functions are going to be, we'll have some situation like, basically, we'll make it y equals 5x squared cosine of x. Excuse me, so 5x squared cosine of x. Now, with the rules that I know, the rules I have at my disposal, can I do anything to this? Right now. Can I use the power rule on it? Yeah, the cosine, basically, as it currently says right now, you're all stumped because there is no way right now, with the rules I'm given, I can handle this. Okay? The power rule, for example, is only going to work if x is by itself. Is x by itself here? No, it's got this cosine of x in the way, right? The rule I've got for taking the derivative of the cosine is only going to work when it's the cosine by itself, okay? Not cosine with an x squared out in front of it, okay? There's also no easy way I can separate these two things out to be something like using trigonometry or using polynomials or any of those methods at my disposal. So I have to have a new rule to figure out how to deal with this. And it turns out what we do. There's a rule called the product rule. That allows me to handle something like this here. How the product rule is basically stated is when I've got a derivative, or I'm taking the derivative of two functions that are being multiplied together, which is what I could treat this as. Okay? F of x times g of x. The result, it's kind of weird, but but basically it's the first function kept the same times the derivative of the second function plus the second function kept the same times the derivative of the first function. Okay? So, and when that's the rule there. Okay? So it's so kind of following along up here, how I handle this one, take its derivative, following this rule. Well, the rule says keep the first one the same and multiply it by the derivative of the second one. So what's the derivative of 5x squared? So we keep 5x squared the same and multiply it by the derivative of cosine of x, which is negative sine of x. Good. Okay, and then add to it, the second one kept the same, so the cosine of x kept the same, and multiply it by the derivative of the first one, which is 10x. Okay? And so that would end up being my derivative. If I want to clean it up, I can go ahead and do so. Now remember, this was a free response question in the AP. We're done. That's my answer. Okay? I don't have to go any further than that. But just because we want to be good and make it a little easier to read, we'll clean it up. It's minus 5x squared sine of x plus 10x cosine of x. And that's really as far as we'll clean this up. Okay? There's no reason to go any further than that. In fact, really the only thing I could do left, I could factor out a 5x if I wanted to, but is that going to help me with anything?
No.
Not really, no. So we'll just let it be. Okay? But this is how this is the product rule of how you handle things like this. Okay? Any questions on how it works so far? It's going to be just a matter of remembering that this here is the rule. Okay? Whoops. Go back. All right. And that's so it's another rule you have to remember, basically. Okay?
Can you go over how you got that answer? I'm not really.
How I got the answer?
Yeah.
Sure.
Just like, what are all the steps?
So my steps in this case are going to be 5x squared, I'm going to call f of x, and cosine of x squared I'm going to call g of x. Okay? And so the product rule basically says, when I've got a function written like this, where it's one function times another, so in this case f of x times g of x, or 5x squared times cosine of x, then the derivative comes out to be, keep the first one the same. Okay, so this is my, let's get rid of that stupid blue line. Okay. There we go. Okay. Whoa, what did I do? No, go away. Shoo. Shoo. There we go. Alright, so there's my f of x, keeping it the same. Then according to the product rule, I multiply that by the derivative of the second thing. Okay? So that's what the minus sine of x is. That's g prime of x.
Alright, I got it.
Then you add vice versa. So g of x kept the same times the derivative of f of x, like so. Is that clear now what I've done?
Yeah.
Okay? And then I just cleaned it up after that. Yes, Whit?
What about when there's three things we're multiplying by? I mean, is it totally different or is it just similar?
No, you use the same rule. What you're just going to do is take it in steps. You just pair two off, do the product rule to it, and take that result, pair it off with the original one. So it can get really nasty, but it's possible to do. Okay. Likewise, some functions, and here's an example of it right up over here. Some functions you don't necessarily, you can actually do the derivatives in two ways. Okay. I started off with the function y equals 3x squared minus 5 times 2x cubed plus 3x. That function right there. Okay. And I should probably move the camera so it sees it. Okay. And as you can see here, okay, as you can see, basically, you could do it by the product rule directly, okay, which is what this answer is right here. Then clean it up and come down to a regular polynomial like so. Or, because these things are just two regular functions, there's nothing crazy about them, you could actually multiply them together at first, okay? Then take the derivative of them multiplied together using the regular power rule. And notice my answers were the same. So this answer I got using the product rule, This one I got by multiplying first, then doing the power rule. And my answers end up being the same. So you can have multiple ways of doing the same question. Okay? So there are.
You should have a class where you teach them live
Try a full out
like a live broadcast.
live broadcast.
Yeah.
Preferably an 8 o'clock class.
I kind of creating some sort of like learning space together. I'd be willing to try that out for like maybe like a test review.
Yeah.
Okay.
You can do it from your house too.
Yeah, because I could stay at home and just do it. Do the test review. Or I'm also willing to try that after the AP exam. Okay. I'm not willing to try that for a regular class until after the AP. Because once the AP comes around, we'll still have class, but
It'll be fun.
it'll be a lot more relaxed.
Khalid will be the only
Okay. Especially because you seniors won't take exams. Juniors and sophomores
Obviously,
have to do an exam, but the exam is not bad. Okay. The exam is not bad.
Would we pass it right now?
No, because you don't know any calculus right now. Well, hardly any calculus.
We know the power.
You know power rule.
How
And
far would
private
that
one.
get? How far would that get us? Like through the first page?
Of the AP?
Yeah.
Probably not even that.
Oh, Lord.
Because they don't
It'll get us
divvy it
three,
up by
right?
subjects, they just throw it all together. Okay, so
that's 3, right?
go. Your first question could be like doing the area under a curve question, and that's an integral which we haven't even touched yet. We're not going to touch till January. So,
Fantastic.
The first material is going to be in January that we're going to need to know for the AP.
no.
It's just not in order.
Robert.
An integral
Alright.
is
He's okay.
isn't an integral a derivative of area?
No. An integral is actually called it's based off of something called the antiderivative. And so it's doing this process we've been doing here in reverse, backwards. Okay? That's what the antiderivative is. And the integral itself is doing something fun to the antiderivative. And one of its uses is to calculate the area under a curve. Okay? Just like one of the uses of the derivative is to find the slope of a tangent line, integral tells you areas and things like that. Okay? We'll go over all that, trust me.
Very elementary.
Alright, so we saw how multiplication works. Let's see how division works, okay? That's our next big thing. So, again, if I did an example, if I had something like, 10x cubed minus 3x over the sine, or 5 sine of x, okay? With my current rules, can I do anything with this?
You could probably modify it to use a power rule.
Okay. Well, how would I modify it that way? If I tried it, I'm still going to have that sine of x in the way, won't I? And then the power rule is not going to work. Nor would the product rule work, because when I bring that sign upstairs, remember it's going to be assigned to the negative first. Okay? Actually, the whole thing would be 5 sine x, all in parentheses, to negative first. And again, we don't have any method to handle that yet. Okay? So, unfortunately, again, it would seem like we're stuck. Well, we're not stuck. We're going to learn a new rule called the quotient rule.
Yes.
Now we're through the first page.
Now we can do the first page of the AP. I like that. Okay, quotient rule. I think I spelled quotient wrong, but whatever. I-E, not E-I. Let's fix that. Quotient rule, there we go. Okay, quotient rule. Basically, the quotient rule is just like the product rule in that when I've got one of these derivatives, okay, basically, again, I have a special way to handle them. In this case here, the quotient rule, it looks nasty, and it kind of is, but it comes out to be you take the bottom, leave it the same, multiply it by the derivative of the top, then subtract the top kept the same, but multiply it by the derivative of the bottom, and it's all over the bottom squared. Okay? So again, I said it was kind of nasty looking, and it is. Okay? So applying the quotient rule to this one right here, okay? If this is my function, its derivative is going to be bottom times the derivative of the top, which will be 30x squared minus 3, minus top times the derivative of the bottom. What's the derivative of 5 sine of x? It's 5 cosine of x. Good. All over the bottom squared. Okay? And so if it helps, there's f of x, g of x. And this here would be g of x, f prime of x.
Are we gonna be given these formulas on the test?
Nope. Sorry. And you can see there in blue, there's all the pieces. Yes. Okay. All right, that's your quotient rule. Okay, in use. Quotient rule is not going to be as friendly looking as I'm not going to have an example like this that works with the quotient rule. I kind of could. If you look over here, I have written up there a rational function x cubed minus 3x squared plus 2x minus 4, all that over x plus 1. If I took the derivative of it using the quotient rule, I'd get one answer. I'd get the same answer if I used division on that first and then took the derivative, but is that going to make more work or less work? More. Much more. Okay? Especially because I believe at the end you're going to have a remainder that you're still going to have to use the quotient rule on. Okay? So, it doesn't really help you, does it? Okay? And so, but notice, you can do it an alternate way if necessary. Now, the quotient rule has a fun little mnemonic that people use to remember it. Okay? That makes you sound like you're in the Swiss Alps when you're yodeling. Okay? You're yodeling in the Swiss Alps. Okay? The quotient rule, the mnemonic for it is low D high minus high D low over low squared. Basically, low D high minus high D low over low squared. Told you it sounds like low.
That last part's not really good.
What, the low squared? Yeah. But the low D high minus high D low. Yeah.
Over low squared.
Sounds like you're yodeling. Yeah. Basically, that's mnemonic, and again, low means the bottom, D high derivative of the top, minus high is top, derivative of the low, bottom, over the low, bottom squared. Okay. So, low D high, high D low, low squared. Oh yeah. Okay? I didn't think you would sing in math class.
Big yodel in this right now.
Can I yodel? I don't know. I think yodel, is it yodeling just like making noises while?
No, it's an art.
Singing from your chest.
Probably. Isn't it all singing from
We
your
get
chest?
there like 7.
Singing from your stomach or something is crazy.
Well, I do know that my thanks to being in a musical over the summer with the 4 county players, the local play group. If I learned anything from them, I actually ended up learning what my vocal range is. So when I sing, I'm a bass, very low apparently. So
How old is that?
Robert, aren't you that way too?
I've got like a really high singing voice.
Is that a good experience?
I'm a tenor.
oh, the 4 county players, yeah, it was fun. Interesting, a lot of work.
What are you, Tommy?
All right.
You're a wild card.
Any questions on how the quotient rule works? Okay. What we're going to add today, in addition to the product rule and the quotient rule, let's go ahead and take a look at 4 more special derivatives. Okay.
So read 4 more rules.
No, these are special derivatives.
Perfect.
So far.
Groovy.
I should do the
Just more is better.
More special derivatives. Okay, so the 2 special derivatives we know right now are the derivative of the sine and the cosine. Okay. The thing is, are those the only 2 trigonometric functions?
No.
No, we have others, right? How many total are there? There's 6. What are the other 4?
And
Tangent, cosecant, secant, cotangent, right? Well, we want the derivatives of all of them. The thing is, I can actually derive the derivatives of all of them right now because I know the quotient rule, okay? Because, for example, if I wanted the derivative of the tangent, okay? Derivative of the tangent of x, well, what's the tangent? It's what over what? Sine divided by cosine, right? So I could do the sine divided by the cosine, do the product rule to it, and get the derivative that way, right? But it's a lot faster, especially if we're going to be using a lot, just to memorize what it's actually equal to, okay? And to treat it like a special derivative like the sine or cosine, okay? And it turns out they always come out regularly. So the tangent of x, its derivative is the secant squared of x dx, okay? Now, these guys as doppelgangers, the cosecant, the secant, and the cotangent, also all have special derivatives. Again, we could derive them all using the product rule, quotient rule, excuse me. We could derive them all using the quotient rule. Since, what's the cosecant? It's what?
1 over sine.
1 over sine. What's the secant?
1 over 2.
And what's the cotangent?
1 over 2.
1 over tangent. Okay? And since we know these, we can do those using those methods. But again, it's a lot easier just to know what they are. Okay? And so, the derivative with respect to x of the cosecant of x is going to be equal to minus the cosecant of x times the cotangent of x. Dx, okay? The derivative of the secant of x is going to be the secant of x tangent of x dx, okay? And lastly, the derivative of the cotangent of x is minus the cosecant of x squared, or minus the cosecant squared of x dx, okay? So, these other ones are not pretty, but it turns out there is kind of a twisted logic to them, okay? For example, tangent of x went to secant squared of x, so the cotangent, it's flipped basically, is, you can think of it the opposite of the secant, which is the cosecant, not opposite, but the other one, the other side of that equation, okay? Instead of secant, it goes to cosecant, and it gets a minus sign in front. In fact, look at this, the ones that are cosine, cosecant, cotangent, they're all negative. Cosine is negative sine of x. Cosecant is negative cosecant cotangent. Cotangent is negative cosecant squared x, okay? So, there is sort of a twisted logic to them, okay? The cos get a minus sign. The ones that don't have the co in front don't get the minus sign, okay? The tangent and the secant are related. The cosecant and the cotangent are related, okay? So on and so forth. So if you look at these and memorize them or learn them by looking at common features or things they share, it becomes a lot easier to figure out what they are. So for example, if I learned the secant is derivative of the secant is the secant tangent, okay? I could then say, okay, the cosecant's the one where I flip everything around and put a minus sign. So the derivative of the cosecant then must be minus cosecant cotangent. Okay? Does that make sense? In a twisted way, it does. Or if it doesn't make sense to you, find your own little way of figuring it out, because there's plenty of ways to do so. Okay? But now, these are all 6 trigonometric functions and their derivatives. Okay? And what we'll do Monday is we'll take some time, we'll go through and we'll show how we get these 3 from using the quotient rule. Okay? Or you could do that for homework. I might just put it as a homework assignment. Yeah?
Are we ever gonna have to like solve like on a test, for example, like how to figure out how to get from like secant of x to, we have to solve on the derivative of it, are we just gonna work it out, or are we always just gonna be able to?
Oh, you can always just use what you know.
Alright.
So I guess the question would be like if I had something like, if I just told you give me the derivative with respect to x of 3 secant of x squared, well, the derivative of the secant is the secant tangent, so this would be 3 secant of x squared tangent of x squared all times whatever the derivative of x squared is, which is 2x. So 6x secant of x squared tangent of x squared. Okay? You treat it the same way you would do the sine of the cosine. Okay? That's what I'm getting at. Okay? It just recognize that it's got a bigger part to the derivative. Okay? Any questions? All right.